Okay, well, hello everyone. So my name is Alex. I'm a PhD at Wageningen University, and I'm here to talk to you a little bit about the definitions and developments in explainable AI for Earth observation. So first off, I think it's important to mention that this presentation in almost its entirety is based on a review paper by Caroline Gevaert from ITC Twente. She wrote a paper about this that I had the pleasure of reviewing. It's a really good paper. If you're interested in this topic, I would recommend that you read it. So full credit to the author on almost anything that I'm presenting here. So with that in mind, quick look at the content, what I plan to discuss. So firstly, briefly on outlining explainable artificial intelligence. We need to talk about definitions and figure out what exactly it is. Secondly, what I want to do is immediately discuss sort of the legal context, which sort of frameworks, which kind of regulations come into play when we talk about explainable artificial intelligence. Then I want to talk about the perspective that the social sciences have of explainable artificial intelligence. Then a little bit from the technical perspective, what can you expect when you actually go into explainable AI? And then finally, once with that background in mind, we take a look at what explainable AI for Earth observation itself actually is. And lastly, I will close with some take-home messages briefly summarizing what we have talked about. So maybe people here are unaware of what AI it exactly is. In a nutshell, you would say that AI is essentially taking predictive statistics, such as these funky little linear regressions that you might remember from high school or your early college statistics course. If we take a whole lot of steroids in the form of smart people, statisticians, and in some cases madmen, you would end up with hard to understand but powerful models, which should, in theory, mimic the brain. In practice, really do not. They are supposed to mimic the brain, but there is no emergent intelligence. So just because of the fact that, hey, it's artificial intelligence, you should really just consider it an overdose of predictive statistics. So in the end, we're still talking a lot about what exactly are statistics and how does it relate to us being able to get more information out of aerial images and everything else. So what is the fundamental need for explanations? Why should we, in principle, care about wanting to explain our computer models? I mean, if we get R squared, if we get a performance of 90%, that's really good. Why should I care about wanting to explain my models? Well, from the concepts of psychology and parsimony, we have, or statistics, we have simplification and parsimony respectively, which essentially boils down to the same idea, and that is that you want to keep it simple. Occam's razor, where the simpler option is usually the better option, so long as they have like an approximate solution, an approximate, how do you say it? Yeah, approximate performance, approximate solution. Other than that, explaining things is part of human knowledge transfer. We understand the world around us by pitching hypotheses about the world, like, okay, I think the world is flat, and then you can exchange that with no, because this is why the world is not flat. It's part of how we exchange information as humans. So, quite really, is it explainability or interpretability? This is often a question that comes up, and this is sort of the slide that if you were in the field of explainable AI, you would recognize this because people use these words interchangeably. But let's see if we can make some sense of the definitions which are commonly used in the field. So what is an explanation? And you can most easily see that as a degree to which an observer can understand the cause of a decision. So in this case, you can see if you as an onlooker are able to understand the reasons why a model came to a certain decision. The second one is a little bit more in depth. It's disentangles interpretability, which from interpretability from an explanation. And the core concept here really is that you want to relate it to domain knowledge. So you want to be able to explain why things are using common knowledge instead of saying it is simply the case because we have information on these pixels, or because the model thinks this is important in the thing. No, we start to relate it to domain knowledge, such as in the case of phenology or something, the greenness or the type of plant, these kind of things. So for Earth observation, a common take-home message is that we shouldn't forget about domain knowledge, and this will come into play later. So interpretability, explainability, sort of the same thing, depending on the field, it might be different, but in Earth observation, we are actually able to set definitions for them. Okay, that's great. So explanations are supposed to give us all these wonderful things like knowledge transfer and better, more transparent models, but why aren't we doing it? Why don't we make interpretable models in the first place? And part of that is intentional concealment. And one of the things that you see often in the big artificial intelligence conferences, for instance, is that people promise to release their source code and few ever do. And if they do, it's often messy and the results are hard to reproduce. So intentional concealment is something that should be suspected. Secondly, there's literacy gaps, where more common users or people that are not experts at the system are simply unable to understand it because they cannot reason in the way that these models work. This is another common gap that we have in our understanding of like models which become so complex that you cannot simply look at a bunch of statistics and understand why decisions are made. And that comes down to the idea of three-dimensional thinking. Humans can think in 3 dimensions, and most AI models are able to interpret thousands of dimensions, if not millions. And that simply becomes more difficult to understand what is going on then, because we cannot conceptualize what a 10-dimensional space looks like, for instance. So we need to simplify it to create methods which can take the predictive power of high-dimensional data and make it understandable for people. A quick footnote on explaining itself is that just because an output is interpretable, it doesn't mean that it's useful. And you see a little bit of a verbose quote here, but useful in this case might not be sufficient to satisfy the legal frameworks, which are becoming increasingly important, or simply even the person that asked the question. If you give an explanation for something, it might still be rubbish. So another concept that's important is model fidelity, and that essentially tells you how complete is an explanation. Is an explanation a very gross simplification of what a model actually thinks, or does it try to more fully capture the entire reasoning process of a model? So if you want to quantify this, you get to the concept of model fidelity. So next up, I want to talk about the legal context for explainable AI, where I think this is sort of the meat on the bone, because so far it has been nice to have. You will have a lot of people that care about understanding and learning from our models, and then there's a whole group of people that say, I don't care, I just want my 99% accuracy on whatever benchmark you want. Well, surprise, surprise, we're going to the case where AI models are actually going to be fairly strictly managed in the frame of law. And that's a regulatory context. So first off, I want to talk about the UNESCO recommendations for the ethics of artificial intelligence. And these have an emphasis on low middle income countries, which tend not to have much of a grasp on artificial intelligence. And they sort of outline values or important principles. It's more of a guidebook than a legal framework, and it provides recommendations. But still, the fact that it came into existence should be a warning that, hey, this is a prelude for laws which will actually restrict the things that you are able to do with artificial intelligence. And speaking of restrictions, a very interesting trend to watch is the European Commission draft Artificial Intelligence Act, or AIA for short. And this focuses on the EU internal market. But as we know, the European Union has 730 million inhabitants, so it has quite a lot of punching power, the same way that the GDPR has also inspired other countries to adopt their own privacy laws. The aim of the AIA is to provide strong protection for the public for AI application domains in order to make sure that draconic measures such as a social credit system or similar measures which can severely harm the human rights of people are not under consideration for artificial intelligence programs. And the most salient thing about this is that it will enforce an adherence to the framework, meaning it will become legally binding once this act is actually in effect. So in order to, how do you say it, adhere to these sets of regulations, one of the things that you need to be able to do in extension to the GDPR is actually explain your predictions. And I'll get to that in a second. So the main takeaways of the AIA are really it focuses on the development, use, and uptake of artificial intelligence in order to provide a high level of protection of the fundamental rights of EU citizens. And I mean, you can read the full quote, you can read the document in full, but essentially another salient point, specifically relating to explainable artificial intelligence, is that they also need to be sufficiently transparent, and that means that you need to be able to provide explanations. And one thing about AI models is that out of the box, they provide you with no explanation, or most of them don't anyways, and there's very few that do, and when they do, it's not particularly reliable. So the point is, this will become legally binding. You need to be able to provide transparency to your viewers, to your users. And this will become a very important point of EU policymaking. And I can assure you now that in 5 to 10 years from now, you will have positions sort of as like AI privacy officer or AI adherence officer, in order to make sure that that companies and models are adherent to this AIA. So how do they plan to do that? Well, one of the things is that they try to define 4 risk categories. So risk category 1 is an unacceptable risk, which is a social credit system in the way that it's currently active in China, which is deemed to be incredibly intrusive and discriminatory, whatever else you have. This is the clear example that's given by the European Union. There's high risks such as remote biometrics, face readings, for instance. These are subject to legal restrictions. Limited risks such as deep fakes, the funny pictures of Boris Johnson on video call or whatever have you. They need to you need to disclose that you are talking to a deep fake or a chatbot or anything else. And finally, there's minimal risk, which is anything else essentially. It's the way to interpret this act is that it is the right to an explanation, which was already in the GDPR, but it has become actionable. And when will it become actionable? 24, 25. So in 2.5 to 3 years from now, we will have a legally binding framework, and that is going to be a pretty big deal in how people use these kind of models. So that's definitely one to watch out for. There's some criticism for the draft as well, where some of the required explainable AI demands cannot be met according to the state of the art. So when it comes into force, there's going to be a period of leeway. There are wordings for ethics washing, where you can say, okay, the wordings are not accurately depicted just yet, and they need to be refined more. And the explanations are focused on the user, but not so much to those affected. And there's an entire debate on how we should frame this act, but I wanted to show a little bit that this act is not the end-all be-all, and we should want to discuss more about why we need to provide transparency with our AI models. Yeah, there's also a little bit on explainability metrics, but for the sake of time, I will skip this slide. And I will go then to the social sciences perspective. Now that we have established that it is necessary and that it is valuable for human knowledge transfer, we need to understand, but what do the social sciences think? Because they have been reasoning, theorizing about how humans exchange information. Surely they have ideas on how models should be able to do it too. There's a couple of main takeaways that we can see from the social sciences perspective as summarized in the original paper, which I'm presenting work of. According to Tim Miller et al., human explanations are contrastive, meaning we tend to compare things, we tend to compare solutions, and we see, okay, well, which one fits better? Human explanations are selective on a subset. We do not consider 100 million examples. We consider a couple of well-selected representative examples, and these should tell us what is going on. And finally, human explanations are, and I'm coming back to this idea already, they are essentially knowledge transfer. We should be able to learn from what an explanation is. And this comes into play a little bit later when I talk about how it's related to artificial intelligence for Earth observation itself. But I wanted to highlight the fact that yes, knowledge transfer really is a big deal in the idea providing explanations. So where do the social sciences think that artificial intelligence at this point can improve? And I mean, let me put it this way, there's a lot of criticism on the current state of the field because a lot of it is it's biased towards performance, meaning that most papers do not compare to a simpler but more elegant baseline, which actually tells you what your model is doing. In that same sense, we do cherry picking to show that, yes, our models work fantastic. They can provide you with the exact explanation that you want. And oftentimes, papers and models do not give you representative samples. Finally, there's a need to quantify the descriptive accuracy because we work so much with numbers and this whole field is describing data sets of tens of thousands, hundreds of thousands of aerial images. We need to better be able to describe what is a good answer or not. And in that same spirit, a more minor note is that causes, so being able to say this causes this, is more useful than probabilities. To say, okay, well, there's a 90% probability that something happens. That's nice, but that's not the way that humans intuitively reason. So as an explanation, it is inferior to saying this has caused this. So moving on from that, we can talk about the technical perspective a little bit. I can talk a little bit about, well, what sort of explainable AI do we do already? Okay, AI is black boxy, but how do we try to understand this black box, or how do we simplify the black box? So there are a couple of ways to look at it. When you look at a row, you see a type of category, and then in the columns, you have sort of the options that you have for it. So when you look at the design of a model, you have the idea of either building it into the model itself, which we call intrinsic. In that case, you make options available in the architecture or in the model itself that can tell you, okay, these are the things that matter to the model. Then there are post hoc methods, where post hoc in this case means after the fact. So we say, okay, the whole thing is used as a regular model, but we look for explanations after the whole model itself has been trained. Then you have the application, which are model specific, as in, for instance, if you have a specific type of AI model, can you only use it for this, or can you use it across all possible models? And if it's the latter, we call it agnostic. If it is only usable for one type or a small subset, then we call it model specific. And finally, we have the scope, where we have either global methods, meaning they explain why entire populations of samples come to a certain decision, or you can have local methods, and this takes a single data point, a single aerial image, and it tries to explain, okay, why is there an airfield here? Well, because there's a large tarmac strip or something. And with a global method is, well, what is an airfield exactly? All airfields have a long strip of tarmac, for instance. So this is the way you can interpret global/local. This comes into play a little bit later when we talk about which methods are actually used for Earth observation itself. First, though, why do we actually do explainable AI? What are the purposes of it? Well, we can use explainable AI to justify the performance of our model, to say, hey, our model has 90% accuracy because genuinely it finds the right answers, and you look for explanations to justify what a right answer is. Then you have control, where you try to look for problematic samples where your model's explanation is really off. You look at it as a way to troubleshoot problems with your dataset or your model itself. Then there is explain to improve, where we take the ideas generated by a model, which says, okay, well, if this particular parameter, this particular part of the dataset is really important in order to predict this particular type of thing. Like greenness is incredibly important for recognizing vegetation, right? I mean, this is a very obvious one, but if somebody doesn't know that something contributes very strongly to something, you might want to use these explanations to improve your data set or to train your model to focus more on these. So you can use explanations to improve your own model. And finally, there's fundamental knowledge discovery, where you use explainable artificial intelligence to discover new ideas, to learn about a topic. And personally, I think the latter is incredibly important because there's a lot of vaporware in the AI space where you train a model and you don't learn anything, you just beat the benchmark. So I think explain to discover is my personal, how do you say it, most important one. But all of them have their own reasons and their own reasons for existence. So where do we currently stand if we look at Earth observation? Because all I have talked about so far is what is artificial intelligence in general and like what are explanations. And I mean, this should give you a pretty good idea about the general state of the field. And now let's try to go a little bit more in depth on what that does for Earth observation. So for this, I want to briefly give a history of Earth observation and AI in general, to be honest. For those of the people that have more of a GIS background or might not be up to speed with really what's happening in Earth observation. So when we look at early Earth observation, we talk about the Landsat series of satellites, which were fantastic for monitoring things like vegetation, and they fall short on, for instance, monitoring urban areas, where 30 megapixel resolution is simply too complex. Then we have a period where you see incremental complexity, such as more sensors, better resolution, and simply more data sets and more ideas being generated from this. In the early to mid 2000s, you can see then that predictive analysis actually start to happen. And I use a picture of like a decision tree because, well, the first thing you, as sort of like an Earth observation person that comes to mind from this period is, oh yeah, that's right, we used a lot of random forests and we used a lot of decision trees. And this is sort of when machine learning got its first footing for sort of on Earth observation itself. And to this day, these types of machine learning models are very, very commonly used, and with good reason, I might add. We are currently in sort of the past 6-ish years. We have come to the phase where we are able to make deeper and more complex models. We are able to take advances from computer vision since the beginning of the last decade, and we're able to translate them slowly but surely to the field of Earth observation. It always lags behind, and this becomes an important point later when I talk about the recap, but Earth observation is always behind regular computer vision because the task is harder than looking at photos. That's where we currently stand. So a gradient that you should want to see in development is that it starts very transparent. Everybody can understand NDVI when it's drawn on a drawing board. It's very simple. A random forest, okay, I can still look at for instance, the entropy of each node, but as you can hear, it already gets more technical, and I reckon that half the audience doesn't really know what I'm talking about. And then when I talk about the deep neural networks, okay, try to imagine a 2000 dimensional space. It becomes impossible. And that's sort of when the models become very opaque and we don't really understand what's happening inside of them anymore. So especially in Earth observation, we are very much still in the dark for XAI. So take this as the intro to the actual talk about what kind of Earth observation for XAI we have. So I talked about the categories of explainable AI that we have, where, okay, you have explain to justify, where we first try to understand, well, is the model performance really as good as it is? And you can see that this is also the least commonly used one in the number of publications, which you can see on the left-hand side. And for context, the author of this paper has gone through 100 papers, if I'm not mistaken, and summarized sort of like try to bin each of them in the particular category, which we see here. So explain to control, which was about debugging and trying to find problems in your dataset, is the most commonly used type of explainable artificial intelligence, or the most commonly used purpose for Earth observation. After that, it's explain to discover, where knowledge discovery comes into play, and finally explain to improve, where we try to generate new ideas in order to use in our model itself. So you can see that overwhelmingly in Earth observation, what we deem to be the most important part is troubleshooting and improving our data, or at least that's the current state of the Earth observation field. So then finally, if we look at explainable artificial intelligence for Earth observation specifically, which types of models, which type of options do we have? Because I mean, so far it has gone very largely in abstract detail, but what is actually relevant for Earth observation and which things come up most often? Well, Caroline Gevaert defines four main categories of importance for Earth observation. The first are the interpretable models, and interpretable models themselves are either models which are simple enough to understand out of the box, where you don't need to change anything, such as, hey, a linear regression. You look at the weights and you understand what's going on. It's simple, it's easy, you can understand it, no problem. And then the other category is where we open the black box and we try to understand what's happening inside of it. So these are the models which you specifically adjust in order to get some sort of information out. So then we have the domain knowledge models, and I think that these in particular are the most prominent ones to watch out for in the next decade or so, because a lot of effort has gone into understanding why domain problems, such as, hey, climate forecasting, for instance, there's already physics models which exists for this. What is the role of these physics models for predictive analysis on time series, for instance? And this becomes a pretty big deal where you want to understand sort of which things affect one another. And these sort of physics-driven models really are the most upcoming models that I see in explainable AI for Earth observation, and rightfully so, they have their own category. Then, as a bit of a blast to the past, we have the good old feature selection and feature ranking problems, where we see, for instance, the random forests where, okay, because you have a measure of entropy, which can tell you how good a decision is, you can fine-tune which things to use inside of your model, which things matter, which things don't. So this is also still a commonly used explainability method. And finally, we have saliency maps, and I will explain in just a second how that looks in practice, but the idea of a saliency map is that you look in the pixel space itself and you highlight with like a color gradient or what have you, you highlight which parts of the image are important in order to come to a certain decision. And they are, how do you say it? In common computer vision, they are a commonly used method, but not common enough to warrant them in their own category. But in Earth observation, they are so incredibly common that, yes, I agree with the author that they deserve their own category for Earth observation. So quickly to recap, interpretable models, they are either open black box models or they are inherently interpretable. There's no clear cutoff point for when a model stops being interpretable. We don't have that defined. So when is a random forest still understandable and when does it become a black box? There's no clear answer to that at the moment. Domain knowledge, as I said, mostly physics-based machine learning, but also using established patterns in order to guide the model to better predictions. Feature selection and importance, where you look at whatever goes in, how important is it in order to understand the final decisions. And lastly, saliency maps, which do require a bit of explanation. They are usually looking at which parts of the image the model is most triggered by. What is it inspired by when, for instance, on the left-hand side of the image on the bottom, it is asked, okay, how important is it to, like, which pixels are important to understand the concept of a dog or a cat, or I think that's a dog on the right. And this gives you a local explanation. But as you can imagine, these are not suitable for all tasks. But in the context of Earth observation, you can, for instance, imagine, okay, somewhere in this image, there's an airfield. Can you explain why? And the model might highlight, okay, there's a long tarmac strip over here. So how often are these methods used at the moment? Well, one of the things is the interpretable models are still very common. And this is in part because people still tend to use a lot of random forest models. They were the previous gold standard for prediction, and a lot of my colleagues actually still use a lot of random forest models because simply they make sense. But they count as an interpretable model and you can actually make efforts to understand them. So then we come to the domain knowledge models, and at the moment, or at the time of the review, only 2 papers have been found. And I know personally that there are a little bit more of these domain knowledge models than that, so I think this statistic should be a little bit higher, but okay, maybe it falls outside of the scope of what the author has studied. But I would essentially say, okay, there's only 2 papers that the author has assigned to this bin right now. But I would say watch this space, because this is a very, how to say this, if you look at the people in the field which are promoting this idea, you understand that this is becoming a very, very big deal. Basically, the head of the lab heads in Europe itself are promoting this as sort of like a spearhead. So keep an eye out for the domain knowledge models. Feature selection and importance, for the same reason as random forest models, they are still very commonly used because it works. You can take a look at how important is NDVI to my particular task by looking at the entropy. So again, we see that Earth observation has historically used a lot of interpretable AI, and now we are coming to the black boxy models, which require a bit of a different approach. But you can see it in the statistics that yes, we still use these random forests a lot. Saliency maps, there's 5 papers that the author has identified, and if I go through my stack of reviews of the past year or so, I can tell you that this number is in fact higher. Saliency maps are very, very, very commonly used in Earth observation in order to provide explanations, especially on problems which require you to localize or to understand which things are in one single image. So these are a very commonly used method in order to get some extra juice out of your paper, essentially. Okay, so having established that, yes, we use a lot of random forests, that is sort of the main conclusion that we have at the moment. What sort of perspectives do we have? What does explainable AI for Earth observation, what does it really need? Well, what we can tell now is that there's a clear gap between explainable AI models that are developed and user accessibility. We tend not to think about the life of our models after we have published them. There's poor documentation on documents, data sets, models. There's very little understanding of a model once it has been published. And I guess this goes for computer vision in general, but it's a big problem because in the end, few people can really understand the decisions which went into making models, let alone explainable models. Another difficulty for Earth observation is that they require special workflows. Earth observation data is not easy. Conventional computer vision methods are used to having either the perspective of a horizon or the, how do you say it? They tend to deal more with 3D spaces which have depth or which have very discriminative features. And I mean, for instance, as you can see on the background behind the PowerPoint, this might not be the case for Earth observation data. It requires special workflows, and the field always lags behind in adapting common computer vision methods to Earth observation itself. Meaning, if computer vision is already behind on meeting the 24-25 deadline for the Interpretable AI Act, this becomes a big problem because Earth observation is even farther behind than that. So there's definitely some catching up to do in order to make sure that we meet these deadlines. For the social sciences perspective, what do we need to provide good explanations for society? Models still focus too much on features and examples and not so much on selected arguments. The idea of counterfactuals. You say, a leaf is green because it's or a leaf is a leaf because it's green. Okay, but you can also have brown leaves, for instance. You present counterfactuals. This kind of selection process where you present an argument and you select a counter argument is a big deal for computer vision, but it is underdeveloped, and especially so for Earth observation itself. We can see that 34% of explainable AI papers are benchmarked, so their performance is checked against simpler and more interpretable models. And there's an asterisk behind it because the people that do Earth observation and that have paid attention will know, okay, but this is because we compare stuff against random forests. So this is a statistic which needs to be mentioned, but which is skewed because we tend to use traditional methods. And this number is higher than when we look at computer vision in general, where usually the idea is to compare one deep neural network to another deep neural network. Especially so, Earth observation papers tend to present explanations, but they do not consider the audience. Who is supposed to understand this explanation? Do you test this explanation with the people that are supposed to understand it? And speaking from experience, a lot of papers don't bother. A lot of papers don't define the audience for what their explainable AI model should really target. So this is a big problem because in the end you want to actually explain to a certain group of people. You cannot provide one example that everybody understands. So this needs to be defined more clearly in papers and in documentation when these laws come into action. So that leaves us sort of with the question, well, where do we go from here? What do we want out of explainable AI? Well, explainable AI for Earth observation should be mindful of the upcoming regulatory frameworks. And I keep repeating it because it's so important. If you cannot have adherence to these frameworks, well, maybe in a couple of years from now, you're not allowed to use your models anymore. And especially when you look at data providers such as Planet, which do a lot of automated data extraction over Earth observation data, I'm sure that they have people in-house that would be aware of this and that would try to plan for it. So when we look at the methods itself, they should be selected with audiences in mind. And I talked about that just now, but the idea is we need to understand who is supposed to use our explanations and what kind of methods are good for particular audiences. And for that, I want to take you briefly to this flowchart where you could take a look at, okay, well, what should I do if I look at methods and models? How do I understand what kind of methods that I should want to use in order to explain? And I won't go into detail here, but you can take a look at what should you do in the flowchart. And for this, I would recommend that you read the paper. But it's a useful flowchart. I'm sure that people will advance on it and sort of like build a more social sciences oriented framework around the idea of using methods for particular kind of audiences. Speaking of methods, the only good post hoc analysis method that we currently have for Earth observation are the saliency maps, where we look at pixel values and we determine what is important in the pixels of an aerial image or a satellite image. That's great, but for instance, as someone that works mostly with regression tasks, saliency maps are kind of worthless because a lot of these regression tasks require many variables, or they describe a more complex thing than one single thing. And then I cannot use a post hoc method. So a method which after the fact tries to explain why, for instance, my landscape is beautiful. Well, that's a problem. So these are kind of methods where the gap is currently the biggest and where the most advancement is needed in a short amount of time. So going on to the conclusions, the most important takeaway from this whole presentation is that explainable AI models and AI models in general are subject soon to regulatory and societal scrutiny. So far, we've gotten away with the idea of, yes, we can reach 90% accuracy and they're fantastic, and AI hype, and basically because we are in an AI summer, that's great, but soon it will come to the fact that, okay, but which kind of fundamental rights are we actually treading on when we deploy these models? So this becomes a big deal when regulations are actually coming into play. So the Earth observation community, they should adopt, but also adapt explainable AI methods from computer vision. This is being done, but the speed at which it is being done is not that high. There have not been very many new methods being presented in the past couple of years. And this should really happen because there's a couple good ideas that are floating around in that space. So data sets should be better documented to survive scrutiny, because currently we don't do enough of that. They are lacking in addressing non-expert audiences in particular, meaning that, okay, we can provide explanations that another remote sensing expert might explain, but when you present them to somebody that needs to make the policy, they might scratch their head saying, I don't understand what this is supposed to be based on. And finally, there's more diversity for post hoc methods needed. So methods which can explain predictions after the fact, because this is one of the methods which are going to be useful in order to test models which have already been made, which are in production, but which still need to be tested against legal frameworks. Brief slide presenting the resources. If anybody has any questions about them or anything, let me know. And this is the end of the presentation, and I would like to thank you all for paying attention, and yeah, the floor is open for questions.